Okay, so now what we're going to do is start to actually apply uh, the, the concept of mole to chemistry. Um, and so there's going to be lots of stuff here. So, first of all, we're going to go over atoms, molecules, um, and moles, and the relationship between those and mass. And then from there, we'll go into using this to help us to figure out the uh, the chemical formulas from mass composition, and then we'll get into stoichiometry. And so this is where actually we do probably the most amount of math in the course. There will be different ways you can do the math, and I am going to go over those. I'm not a stickler on technique. A lot of chemistry teachers are. They strongly believe that you should do the chemistry problems in a very uh, specific way, and I understand that. The issue is that you often can get caught up in just doing the method without understanding the what's going on. So I am going to be showing you different ways of doing math problems here. And what I really like you be able to do is to understand the problems and intuitively have them make sense, uh, and that's the first priority. Okay, doing the math and the techniques, they're nice. They give you answers, and they can give you the right answers. But again, like I've talked about before, is that you can get the right answer without understanding, and and I'm a stickler on that more than I am on technique. So you'll see things. I might be a little sloppy with significant figures at this point. And again, a lot of teachers are really, really sticklers about sig figs, but what I really think is important are the concepts. And then you can fill in the holes with sig figs as we go along. And we will do that. So I'll be using numbers like 40, 15, and so forth. And we're not going to worry about how many sig figs they have. What you just have to do is understand that these are values that represent actual things. And, you know, whole numbers, I like to use whole numbers. Whole numbers are easy to work with and see uh, and understand. So, and we'll in the problems that you'll get, they won't be as nice and pretty in terms of the answers and be able to do. So you're going to have to sort of extrapolate um, sometimes when the answer and the problem doesn't seem like it makes sense. You still have to be able to do it the same way that you would do it if you had the appropriate. Had things that go to clear. Okay, so let's get forward. I call this mode. Okay, so one of the things I want to go over is something we call groups, and so groups are ways of putting things together. For instance, one might group 12 apples into a dozen. A dozen apples essentially is a group of 12 apples. Okay. In chemistry, we use groups all the time. Moles are an example of a group. One mole is a group of 6.02 times 10 to the 23rd atoms. Items, okay? And these items are usually atoms or molecules. And you could think of a mole as a container that holds 6.02 times 10 to the 23rd, and I showed that in the intro to mole. Okay, so you might think of it as a mole. Here's a mole, and a mole is just basically a container. And in that container are 6.02 times 10 to the 23rd items. Okay, just like a dozen holds 12 things. Okay, so this is going to be kind of a good way to think about um, our our problems. Okay, moles a group and dozens a group. And what we're gonna do is we're gonna work with dozen and really try to get the concept of what's going on with uh, groups and uh, and and then move forward. Now, the groups are nothing new to you guys. Okay, I mean this should all make sense, but also uh, in dimensional analysis, you have something called the conversion factor, and it turns out the conversion factor is no more than a grouping size. So we say that we have if we have a group and it has 15 items, okay? What you would say is the conversion factor, if you want to use dimensional analysis, would be 15 groups for items. So let's say you had two groups, okay? So how many items would you have? It would be simple. 15 plus 15 is, or 15 times 15 two times would be 30. Oh, if you want to do the conversion factor, you would go 2 groups times the conversion factor, 15 items per group. And the groups cancel out and you end up with 30 items, okay? Which is exactly the same thing we did here, okay? Now I'll be using both of these processes, and I'll even start out with another method of doing these. But they give you the same answer, right? This one is more intuitive to me, okay? Because I have group with 15 in it, another group with 15, and if I put the two groups together, I can see I have 30, okay? If I take 15 things out of each one of them, I'll have 30 things all together. This one doesn't really make a whole lot of sense, but in this case it may, okay, but dimensional analysis doesn't always give you common sense. But again, one of the key things about dimensional analysis is it gets units right. And let's talk a little bit more about grouping. So in grouping, there's two processes. You have multiplication, and multiplication is when you ungroup groups, and we'll see in division. Division is the opposite. And this is again, this can be you can do dimensional analysis as well. I'm just showing you how I use grouping, and you'll see how that goes on. But we can also replace it with dimensional analysis. So let's say I have 15 items per group, just like I did before, and I have and I have 4 of these groups. Well, how many items are there? Well, just makes sense. So if you have 15 items, and that's 4 times, you have 16 items. So you do 15 items 4 times. And what do you end up with? You end up with 60. Okay, that just makes sense. Now, what has happened? You have grown your amount in a sense. Okay, you started out with 4, and you ended up with 6. Okay, and so you have multiplied. Okay, your multiply means grow, so your number has grown from 4 to 60. So when you ungroup, okay, when you let items out of groups, okay, remove them from the groups, the number will always get bigger unless there's a one-to-one relationship. Okay, so if you know your group and you want to ungroup your group, the number will always get bigger, all right, and that'll be multiplying. And we'll do more of these. Now, if you want to do dimensional analysis of this, you would say the grouping size is 15 items per group. So you would say I have four groups. Okay, 15 items. Can't write very well. Per group. Okay, the groups cancel out. Again, I have 60. Okay. All right. Now, there's another way to do this, and that's just to do a ratio. So I have grouping, I have dimension analysis, and if you want to do ratio, you would just set the ratio, which is basically this relationship here, 15 items per group equals X items over 60, over 4 groups. Okay. All right, and it's just solve for X. So cross multiply and you get 60. So you have 3 different ways of doing this problem. Okay, one is using group, it's like I did here. You have another one where you could use dimensional analysis, and another one you could use ratio. And so, we use the one that, whatever one that you can come up with the answer, but the answer's got to be right. Okay, division on the other hand, is a method of grouping into groups. Okay, so let's say I have 300 items and I want groups of 15 items per group. Okay, so the way that I would do this, I would take these 300 items, and what I'm going to do is that I'm going to divide them up into groups of 15. Okay, 1, 2, so I just divide them, and when I divide them all into groups of 15, I end up with 20 groups. Okay, and if you notice, when you put things into groups, the number gets smaller. Okay, so you go from 300 to 20. Okay. Now, you could do this dimensional analysis as well. So as you say, you have 300 items. Your conversion factor is the grouping size. And then you have to do it the right way. So it would be one group over 15 items. Okay, cross them out, and you end up with 20 groups. Okay, so here's the grouping method, and here's dimensional analysis. And ratio method, you would say X groups over 300 items has to equal 1 gram over 15 items. Again, and then solve for X, and again it's going to be 20 groups. Okay, so you have 3 methods to do this. You have one that does groups. Okay, you divide. Okay, divide up into groups. Dimensional analysis, and then ratios. Okay. I kind of like this method here because this makes intuitive sense to me. I have 300 items and I'm dividing them up into groups of 15, and then I end up with 20 groups. Okay. All right, so now we're going to go on and, well, we're not going to do that first, but let's take a look at using the mole concept. Okay, so it's time to put the mole concept to use. All right, first you have to understand that when we talk about a mole of substance, we are talking about a specific amount. So a mole is 6.02 times 10 to the 23rd. That should be a 2 there. One of the biggest mistakes students make, included me, I used to, is that a mole represents mass. It doesn't, okay? But it's easy to do this, all right? And so, one of the problems, and I don't know, we'll get into this, but there might be a problem that says I have 4 times 10 to the 27th atoms, molecules of water. And then the problem may be how much does that weigh? Okay, so what is the mass of this? Okay, So a typical thing that students will do, and I used to do this is that they would multiply or divide this by the molar mass, or use molar mass to come up with this problem. Okay, to get this problem. Right? You can't do that. All right. You can't do this. Okay, you can't go from molecules to mass. All right, and just because it's just not there isn't a direct relationship between them. Okay, so so we're going to see that, and that's a problem, and we'll go over that. But before we go on, before we get into the mole, what I want to do is look at doing conceptual problems with dozen. And when you learn how to use this process using a dozen, hopefully you can translate that to use it for moles. Okay, so a dozen represents number 12. In the video, I told you that in the previous video, I told you that words can represent numbers. Like 1,000 is 1000, 10 is 10, and so forth. So we always have words for numbers. Okay, that's just by saying 10. That's a word. It's not a number. And if I told you to write down 10, okay, you probably write down 10. Okay. But I really wanted you to write down TEN. All right. But in math class, your brain translates this word into a number, and you write it down as a number. So it's important to understand we use this concept all the time, word to number. So let's play around with a dozen. So a dozen is an amount, and so you really have to understand that, okay? It's not a mass, it's just a relationship between one amount of material. So a dozen apples and a dozen watermelon are both 12. So that a dozen is a dozen, okay? That's all it is. Doesn't matter if it's apples, watermelons, people, etc. A 12 is 12. So let's just play with this relation, 12. We can write this relationship as 1 dozen apples equals 12 apples, and 1 dozen watermelon equals 12 watermelons. Now, the thing here is 1 dozen is 12. So this equal sign here really means 1 dozen is 12 apples. And that's actually an important point in science. Is equal often means is exactly whatever it is. 1 dozen is 12. But also, the equal sign is not actually an exact connection between the two things, 1 dozen and 12, but it's a relationship, okay? And that really you have to understand that, okay? And we'll get into that when we get into math. So right now, when we talk about amounts, 12 dozen is the same as 12. Okay, it doesn't matter if it's apples or watermelons. So let's do some examples of this. If I have 4 dozen apples, how many apples are? Well, this is easy. I have 12, which is another word for a dozen, and I do that 4 times. And that's going to be 48 apples. All right? I mean, you didn't even have to do that with math, but let's do the math. All right, and I'm going to do it the 3 different ways. One is ratios. So here's my initial ratio, and that'll be the same as my conversion factor and grouping size. So there's 12 apples per 1 dozen equals X apples per 4 dozen. And then simply solve for X, and you get 48 apples. Now, I'm assuming that all of you are fairly good at math. That's why you're taking this course. Okay, dimensional analysis is another way you can do it. And here's the conversion factor, and again it's the same as the ratio and the grouping size, so it should be the next one. So you have 4 dozen apples times, okay, the conversion factor. You have to have it as apples over dozens. Okay, you could have a dozen over apples, but so that the nope. Oh yeah, so that's right. So you have to have it so the dozen cancel out, and you end up with apples. Okay, and there's 48, and it makes sense. Okay, and then for the grouping method, this is basically the way I just did it here. You have 12 apples per dozen, and you do that 4 times. So ungrouping, so you're taking out of the groups. So you're taking 4 dozen and you're emptying out the apples. So you have 4 dozen, and each one has 12, and you empty them all out. So you do that, empty out 12 4 times, and you end up with 48. Okay. All right. Now, like I said, I don't really care which method you use. To be honest, I like the ratio and the ungrouping, but I use dimensional analysis as well. Okay, it really, whichever one I wanted, that just gives me the answer that I can set up often. If I just want to get the answer and not worry about thinking about it, I will often use dimensional analysis. If I have problem thinking about the problem, have it make sense, I will do the grouping or the ratio. Okay. So one of the key things that you're going to have to do, though, is that you're going to have to show me the way you do it, and you get the right answer, and that includes units. Okay. So I'm going to be using these 3 methods in the problems, but I'll probably just move to ones that just sort of, I expect you be able to figure these problems out as we go along here. So example number 2. Now, let's say I have 120 watermelons, and I want to know how many dozens is. So what I'm doing is I'm taking a bunch of things. Here's 120 things. And what I'm going to do is I'm going to divide it up into groups of a dozen. And I want to know how many groups I have. And remember, my groups are called dozens. All right. So and then there's 3 ways to do it. We can use the ratio. So the ratio is 1 dozen per 12 watermelons, and that has to equal x dozens per 120. Again, solve for x, and you get 10 dozen watermelons. Okay, dimensional analysis, you start out with 120 watermelons. Your conversion factor is 1 dozen watermelon per 12 watermelons. The watermelons cancel out, and you end up with 10 dozen. Okay. And then finally, the grouping, you take 120. Okay, here's your 120. You divide them up into the groups of 12 watermelons per group. That's your grouping size. And you again end up with 10 watermelons. Okay, you use one that makes sense to you, that you like to work with, but again, it has to make sense. All right, and you'll see how, so here we're just dealing with amounts. Okay, so, and we're going to be, we'll translate this idea of amounts to amounts. So we're doing here amounts to amounts. Can't spell. That's supposed to be amounts. And this is a direct relationship. So you're either going from dozen to items, or items to dozen, using some relationship you have here. Okay, next thing is mass. Okay, well, we know that 1 dozen apples and 1 dozen watermelons are the same amount, but they probably don't weigh the same. So let's do this. Let's look at this. And I just want to let you know, I'm using the word weight or weight instead of mass. And that's just because I'm so used to using it I know that weight isn't mass, but but to me, it's translatable. Okay, so technically, I should be using the word mass, and sometimes I will do that. But just remember that when I say weigh, I really mean mass. All right. So let's say I have 1 dozen apples and it weighs 1 kilogram, and also have 1 dozen watermelons and they weigh 5 kilograms. Well, notice here is that both of them are 12 because a dozen is a dozen, but they weigh differently, and that kind of makes sense. I mean, we know apples are kind of small and watermelons are big. Okay. So we could say that 1 dozen apples equals 2 kilograms. Okay. So we have to be careful about this equal sign. This equal sign is not the same as we had before. Okay. So we have to be careful. In this case right here, 1 dozen is 12. It doesn't matter what the item is. Okay. All right. So you have a dozen equals 2 kilograms and 1 dozen equals 12 apples. So which is it? Does a dozen apples equal 2 kilograms, or does it equal to 12 apples? Well, 1 dozen is 2 kilograms. A dozen apples is, I'm sorry, 1 dozen apples is 12 apples. Just because a dozen is a dozen. But 1 dozen apples weighs 2 kilograms. So this equal sign actually should say weighs. It's not really is equal. Okay, so this is what we're doing over here. You have to be careful about this equal sign, because you have a direct relationship, direct, and you also have a relative relation connection. And this is where students, and not only students, but when you're first learning all this, is that you kind of get confused with it, because you either think it's either one or the other. But it can be both in a sense, okay? You have to be careful. You have to pay attention to what we are talking about. All right, so let's go do some problems. Example 1, how many kilograms does 4 dozen watermelon weigh? Okay, I'm going to use different math. So I'm going to be doing the ratio method first. Okay, I know that 1 dozen watermelon from my previous slide weighs 5 kilograms. So I have a ratio of 5 kilograms per 1 dozen. And that's going to equal X kilograms over 4 dozen. And I simply solve for X and I get 20 kilograms. Okay, so 4 dozen watermelon weigh 20 kilograms. Okay, you can use dimensional analysis. You have 4 dozen times conversion factor, which is the same thing as the ratio above, 5 kilograms per 1 dozen, and you get 20 kilograms. And again, using the ungrouping, so you have 4 dozen. Now, instead of putting 12 in here, you're going to put in 5 kilograms. So you have 5 kilograms in each one. And what you do is you basically empty out, ungroup 5 kilograms from each one, and then you get 5 plus 5 plus 5 plus 5 equals 20, or 5 4 times. And they all give you the same answer. So make sure you look at these, okay? Now, again, a lot of students have been brought up using this method here, dimension analysis, and that's fine. But remember, it's got to make sense. So dozens is a group, and you're letting out. So remember, dozen, and we'll even see moles, are groups. And anytime you go from a dozen to something else, will either be mass or amount, you're always going to be ungrouping. So whenever you go from dozen to either amount, a number of items, or mass, you're ungrouping. Okay. So let's say you had, if you had 4 dozen, you want to know how many that is. You do 12 4 times, or 48. Okay, and that's if you want to know amount. And let's say you had 4 dozen, and you want to know how much that weighs. Well, I have to know the mass ratios, and here it's 5. So you do 5 4 times for 20. Okay. So you have to pay attention to what you're looking for here. But anytime you go from dozen to either items or mass, you're always going to be multiplying or letting out, or the number's always going to get bigger. So, and that'll be the same with moles. So if you ever start out with moles, your number will always get, your answer will always be bigger. Okay, 4 to 20, it doesn't. Okay. All right, number 2. How many dozen apples are in 4 kilograms? Okay. All right, so here, dozen, you want to group. Okay. So a dozen is a group, and so you're going to take the 20 kilograms and group them. So now you're going to be taking 20 things, and you're going to be dividing them up into groups to get dozens. Okay, so whenever you want to get a dozen, or eventually a mole, you're going to divide. Okay. But again, there's 3 ways to do this. You can use the ratio, 1 dozen per 2 kilograms equals X dozens per 20 grams. Simply solve for X, you have 10 dozen. So if you have 20, so now to use dimensional analysis, you have 20 kilograms, which you start out with, and the conversion factor is 1 dozen per 2 kilograms. Do the math, the kilograms cancel out, you end up with 10 dozen, right? And finally, for grouping, so you're going to take 20 kilograms, divide each one up into groups of 2 kilograms. So you can divide the 20 kilograms into 2 kilograms per group. And when you do that, you do 20 divided by 2 equals 10. All right. Okay, now what we're going to do is combine the two, mass and amount. So here's what we have. We have 1 dozen watermelons equals 12 watermelons. But we also have 1 dozen watermelons is equal to 5 kilograms. Okay, so you see it. Okay, you see these are saying, kind of look like, which one is it? Okay, is it this or this? Okay, remember that they're actually the same. Okay, this says that 1 dozen is 12. This says 1 dozen watermelons weighs 5 kilograms. So you have to pay attention to what we're doing. And then the same thing you have for apples. So let's say I have 120 watermelons, and I want to find out how much they weigh. Okay, so if you look up here, I don't have a direct relationship between number of watermelons to mass. So I can't do this directly. I can't go from watermelon to mass because there's no relationship up here. I don't have so many watermelons equals so many kilograms. But what I do have is I can take the 120 and figure out how many dozen that is, and then I know how much 1 dozen weigh, and then I can figure out how many kilograms. So this is a two-step process. Okay, and you have to think about this. All right, so I mean, the ones we had before are just one step. You went either from watermelons to dozen, or dozen to watermelon, or dozen to kilograms, and kilograms to dozen. So this one, though, you're going like this. Sorry, I mean, you're going like this. You're going from watermelons to kilograms. All right, so what I'm going to do is I'm going to do these problems using dimensional analysis and grouping. So let's do this problem. So what is the mass of 120 watermelons? Well, first I want to find out how many dozen it is. So this is simple. So you can use dimensional analysis. So you have 120. Okay, and do the conversion factor, cancel out, and with 10 dozen. Okay. Using grouping, so I want to find out, so what I'm going to do is I want to find how many dozen this is. So I'm going to divide the 120 watermelons up into groups. So I divide them up into groups of 12 watermelons, and so I end up with 10 dozen. Okay, so either way I have 10 dozen. 10 dozen. You could use a ratio method as well, using this ratio or to solve it. So the next thing is, you know the relationship between dozen and mass, which is 1 dozen per 5 kilograms. So you just simply, you're using dimensional analysis, 1 dozen watermelons times its conversion factor, and you get 50 kilograms. Okay, using the grouping method, each dozen weighs 5 kilograms. You have 10 dozen. So you take 5 kilograms and you multiply that 10 times for 50 kilograms. Okay. So the mass of 120 kilograms, first thing you did is you found out is 10 dozen. And then you figured that weighs 50 kilograms. All right, example number 2. You want to know how many watermelons 150 kilograms are. Well, you don't have direct relationship between number of watermelons and kilograms, but you can figure out how many dozen that is, and then you can figure out how many grams that is. So first thing we'll do is figure out how many dozen. And there'll be 2 ways you want to do that, using dimensional analysis and grouping. Let me talk about grouping first. So you know that each of that a dozen watermelons weighs 5 kilograms per dozen. So if you have 150 kilograms, so forth, what you're going to do is divide that up into groups of 5 kilograms, and then you'll end up with 30 dozen. Okay. Okay, so this is 150 things over here, and divide it up into groups of 5. Okay, so try to understand that, okay, because that's conceptual. What I'm doing is I'm breaking 150 into groups of 5 kilograms per dozen. So I end up with 30 dozen. Now you can use dimension analysis as well. Okay, so 150 kilograms times 1 dozen over 5 kilograms is 30 dozen. Now I know a lot of students will just go, "Whoa, I don't want to use this because I have to think about it," and I'll just set it up. And I can't stop you. I can't go in your brain and tell you what to do. But I really like you to understand what I'm doing here. All right. Basically, this is what you're doing in dimensional analysis is you're taking 150 and divide it by 5 kilograms. Okay. So this operation here, even though it looks like you're multiplying, when you do this, you just take 150 times 1 dozen divided by 5 kilograms. So you're taking 150 divided by 5. So this is a division problem, and that's what we're doing here as well. But this actually uses the word divide, okay? And it actually makes sense because you're dividing up into groups. Okay, so you have 30 dozen. Okay, now I want to find out how much that weighs. Well, just quickly. So each dozen weighs how much? Uh, well, so I already figured that out. Sorry. So I want to find out how many watermelons I have. Well, just think about it. So if you have 30 dozen, each dozen is 12. You do 12 30 times and you get 360. And that's what the ungrouping is, okay? So you had 12, which is a dozen, and you do that 30 times and you get 360. Okay. That just makes sense. Now, if you want to do dimensional analysis, you would say 30 dozen times the 12 equals 360 watermelons. Now, dimensional analysis, what you can do with that is you can actually combine these two guys together. Okay, and so you could do 150 kilograms. Okay, times the conversion factor of 1 dozen over 5 kilograms. Okay, the kilograms cancel out. And then you're going to have your dozen, which is 12 per 1 dozen. Now the dozen will cancel out. And then you'll end up with 360. Okay. Now, so you're doing 2 steps. You do this step and this step. I broke them up into this and this. Okay. Again, what concerns me is you get the right answer, so 360 watermelons, and you show me your work. You could use the ratio method, you could use the grouping method, you could use dimensional analysis. Next one. So here's some practice problems, and use the ratios that we had from previous. So how many dozen watermelons is 480 watermelons? And I have the answers over here. And go ahead and do these, see if you get it. All right. So let's go back to groups for a second because all of this is grouping. So a dozen is a group. A mole is a group. So anytime you want to find out how many groups you have, you will use division. So, if you have a bunch of things and you want to put them into groups, you're going to divide them up into groups. Okay. So when you want to go into groups, you always divide. So when you make groups, you're going to divide. That's if you're using the grouping method. If you're using dimensional analysis, your bigger number will be on the bottom. Okay, basically. Now if you go the other way to ungroup, so if you want to ungroup your groups, you're going to multiply. You're going to empty things out of groups. Okay, so when you go when you group things, your numbers always get smaller, and when you ungroup, the numbers will get larger. And I think this is important to know. So when we get into moles here, remember a mole is a group. So if I ask you how many moles something is, okay, the number that you end up will be smaller than the number you start out with because you're grouping. If I ask you how many molecules are so many moles, your number will be larger because a mole is you're emptying things out of the moles. All right. I think that's the kind of important things to look at. So pay attention to your answer. If I say how many molecules are so many moles, your number should be bigger. So if you have 4 moles and you want to find out how molecules that is, okay, this number over here will be much larger than 4. Okay, but if you do it the other way, start with molecules to moles, your number will get smaller. So keep that in mind. Okay. All right. Okay, now on to moles. Now we're going to actually use moles. So we're going to do some mole operations. We're going to look at mole amounts, mass, and then amount mass. So we're going to do amount to amounts, amount to mass, mass to amounts, and then combine the two. If you give it a certain amount, what is the mass, and so forth. So start out with amounts. Like a dozen, a mole is an amount. Okay, it's a group. It's a group of 6.02 times 10 to the 23rd. Avogadro's number. Okay, we're going to be just be using this relationship for very small amount of time now. Okay, so but get the idea. All right. So let's start out with a couple examples. So remember, a mole simply is a group of 6.02 times 10 to the 23rd particles. So you can think of a group. So here's your mole. And inside that mole are 6.02 times 10 to the 23rd particles. So number one, how many carbon dioxide molecules are there in 5 moles of carbon dioxide? So remember what I said is that we want to go from moles to molecules. So the number is going to get bigger because you're ungrouping. Okay, so you're letting things out of the moles. So I'm going to do it the conceptual group way, then we'll do dimension analysis. So this is a simple problem. So you know that each mole is 6.02 times 10 to the 23rd. You have 5 of them. And so you're going to do 6.02 times 10 to the 23rd 5 times. Okay, which is 30.01 times 10 to the 23rd. So scientific notation is 3.01 times 10 to the 24th molecules of carbon dioxide. So what you're doing is you're taking 5 groups and ungrouping each one, and each time you let out, you'll let out 6.02 times 10 to the 23rd, and you do that 5 times and you end up with this much. Okay, then you notice the number gets bigger. It goes from 5 to this number here. Okay, dimensional analysis, you set it up, you have 5 carbon dioxide molecules times conversion factor, and same thing. So that's a simple problem. Okay, now let's go the other way. So now what I have is I want to know how many atoms, well, not the other way, but here I'm going to be using atoms instead of molecules. So how many atoms are 5 moles of helium atoms? Again, you're going from moles to items. In this case, the items are atoms. So your answer will be a big number, bigger than 5, because you're letting things out of the moles. Okay, it doesn't matter that it's helium. It could be carbon dioxide. So you'll notice we'll get the exact same answer as we did before, because a mole, no matter what it is always going to be 6.02 times 10 to the 23rd. That's if you're just looking at going from amount to amount. So dimension analysis, there you go. The key thing here is this, is that you can have molecules per mole or atoms per mole. Right. Just like you can say 12 apples is a dozen, or you could have 12 watermelon is a dozen. A dozen is a dozen. I know this used to confuse me. Why do I have you go Shouldn't it just be one or the other, or shouldn't it just be molecules per mole or atoms per mole? No, it's because sometimes a mole is a mole. So you could have a mole of cars. So it could be 6.02 times 10 to the 23rd cars is per mole of cars. All right. So technically this should be 6.02 times 23rd molecules is equal per moles of molecules. Okay, example number 3. How many moles of oxygen molecules are 2.41 times 10 to 24 atoms of oxygen molecules? Okay, here you're going to moles, right? So you're grouping. So when you want moles, you're going to be grouping. So your number will get smaller. So you'll be going from this number and it'll be a smaller number. Okay, so we're going to do the grouping. So first of all, what I like to do is I like to put my exponent in the same exponent as my exponent here. And you know, you don't have to do that, especially if you're using a calculator, but I'm doing this so it makes sense to me. So I'm going to change this to 2.41 times 10 to the 24 to 24.1 times 10 to the 23rd. And you'll see that why that is in a second. So what I'm going to do is I'm going to take this amount and I'm going to divide it up into groups of 6.02 times 10 to the 23rd. So I have this amount and I chop it up into groups of this. And when you do that, so I'm going to divide this number by this number here. And when you do that, the exponents cancel out. So really the only math you have to do is this right here. And you'll see that's simply 4. So what I did is I divided this amount up into groups of 6.02 times 23rd, and it ends up being 4 moles. Okay, so notice here when you go to groups, the number gets smaller because you're dividing them up into groups. And you have 4. And then you could use dimensional analysis, okay? So here's your started, and then here's your conversion, and you get your answer. Again, I don't care which one you use, but show your work and your units. This one here conceptually made sense to me. This one here is just math, a method. A lot of teachers wouldn't even talk about the concept. They would say take 2.41 times 10 to the 24th atoms, multiply it by its conversion factors, the atoms cancel out, you end up with moles. Okay, they wouldn't tell you how it makes sense. What you're doing here is you're dividing it up in groups of 6.02 times 10 to the 23rd and end up with 4 moles. Okay, next example. How many oxygen atoms are in 5 moles of carbon dioxide? So what you have to know is the carbon dioxide is CO2. Now, the second question, how many total atoms? So this one's a little bit harder. So we're using the answer from the last problem. So from the previous problem, we know that 5 moles is 3.01 times 10 to the 24th molecules of carbon dioxide. And you know, for every molecule of carbon dioxide, there are 2 oxygens. So how many oxygen molecules, atoms are there all together? Well, just think about it. If you had 5 people, and how many arms would there be if they're just normal people? There'd be 2 arms per person, so you end up with 10 arms. So if you have 2 oxygens per carbon dioxide, you could see simply is that the number of oxygen atoms would be twice that amount. Okay. Well, how many atoms are? Well, there are 3 atoms in carbon dioxide. There's 2 oxygens and 1 carbon. So you would simply, if you have this many carbon dioxides, you're going to have 3 times as many atoms. So if you have 3 people, and each person has, you know, 3 appendages. How many appendages would you have? You go, well, there's 3 appendages per person, so there would be 9. They're kind of saying the same thing. You have 3 appendages per mole, molecule. So there's going to be 3 times as many appendages. All right, now we're going to go to mass. So this is an indirect relationship between mass and amount, like kilograms to dozen. But we're going to be using grams per mole, or what is known as molar mass. So each substance has its own unique molar mass, which I talked about in the first video about moles. And you should be able to figure the molar mass out for a substance. We went over that. And what I'm going to do is I'm going to use round up numbers just to make the math simple. So let's focus on water. So water has a molar mass of 18 grams. Okay, each hydrogen 1 gram per mole, and each an oxygen 16 grams per mole. Add them all up together, you get 18. So what we can say that 1 mole of water weighs 18 grams. We use the word equal. Okay, remember that just is a relationship. But remember also that this another way of saying this is 6.02 times 10 to the 23rd molecules weighs 18 grams. And what we do is we substitute 6.02 times 10 to the 23rd with the word mole. And if we did carbon dioxide, 1 mole of carbon dioxide weighs 44 grams. Then you can do it the same way. Carbon is 12, each oxygen is 16. And so you get 12 plus 16 is 44. And that's essentially saying that 6.02 times 10 to the 23rd molecules weighs 44 grams. So, so if you have a mole of water, there's going to be 6.02 times 10 to the 23rd waters in here, and they're going to weigh 18 grams. If you have 1 mole of CO2, it also is going to have 6.02 times 10 to the 23rd. Okay, but it's going to weigh 44 grams. Just like my dozen apples weighs 2 kilograms and my dozen watermelon weigh 5 kilograms. So let's do some examples. So the first example is how much does 5 moles of water weigh? Okay, how much does 5 moles of water weigh? Well, so this one I think would be fairly easy. Each mole weighs 8 grams, and you have 5 of them. So that would be 18 grams 5 times 4, 90 grams. Okay, next problem. How much does 5 moles of carbon dioxide weigh? Okay, again, so in the first example, you have moles, and you're going from moles to some other thing. Okay, moles is a group, so you're going to be ungrouping, so your number will be bigger. So water, so each water weighs 18 grams. So you have 5 of them, 90 grams. This time we're going to have 5 moles of carbon dioxide. Okay, now if it was amount, the answers would be the same as example 1. But because carbon dioxide weighs differently, you won't come up with the same answer necessarily. Well, each carbon dioxide weighs 44 grams, and you have 5 of them, so you will have 44 5 times for 220. In both these cases, you're ungrouping, so you have moles, and you're going to something else. So moles is a group, and whenever you go from moles, you're always ungrouping, your number always get bigger. And you could use dimensional analysis as well. There you go, 5 moles times 18 grams per mole, and come with the same answer. Same thing with this. All right, now you're going to go the other way. I want to find out how many moles. So you're going to be grouping. So you have 72 grams. You can divide that up into groups of 18. Then you get 4 moles. Okay. So that's fairly simple. And if you do dimension analysis, you take 72 times 1 over 18. Again, which is a division problem. Okay, 72 divided by 18. So it'll give you the same answer. And we'll do another problem here. How many moles of carbon dioxide are 660 grams of carbon dioxide? Well, each mole is 44. You divide that up into groups. Divide the 666 up into groups of 44. You end up with 15 moles. So in group and one number, example 1 and 2, you're ungrouping. Your number is going to get bigger. And in number 2, you're grouping, and so your number is going to get smaller. Conceptual. This is all conceptual. Okay, mass amount. Now let's combine the two. Let's combine the concept of mass, amount, and then amount to mass, or mass to amount. So how many molecules are 54 grams of water? Now we don't have a direct relationship between molecules and grams. But one thing we do is we can figure out how many moles this is, and then figure out how many grams. And that's what we're going to do. So the first thing is to find out how many moles of water is 54 grams. Okay, each water is, mole of water is 18 grams. So you divide this up into groups of 18, you end up with 3 moles. So you're finding moles. Okay, so find moles. And then, so dividing, or you could use dimensional analysis, you come with 3 moles. Okay, now you know each mole is 6.02 times 23rd. And you do that 3 times, and you get 18.06 times 10 to the 23rd, or in scientific notation, this. So 54 grams is, and it's not equal, it's just saying that 54 grams is 1.8 times 06 times 10 to the 24th water molecules. So first step, you had to go to moles, okay, and then out of moles. And that's typically the kind of thing you'll be doing, is you go to moles, okay, and and the way to do that is divide, or use when you use dimensional analysis, big number be on the bottom, and then come out of moles. So the number gets smaller and then gets larger again. Just pay attention to the concept as well as the math and your units. Okay, example number 2. How many hydrogen atoms are in 54 grams? We're going to use our previous problem to figure that out. We know that 54 grams is 1.806 times 10 to the 21st water molecules. And remember that each in water has 2 hydrogens, so that's like 2 arms. So there's going to be twice as many hydrogen atoms. Example number 3. How many grams of water is 1.5 times 10 to the 25th molecules? Okay, and there's no relationship between water, grams, and molecules. But what we can do is figure out moles and then molecules. So you're going to, first of all, divide the grams up into moles, and then figure out how many molecules from that. So first thing you do is you're going to divide this up into groups of moles to figure out how many molecules to figure out how many moles you have. So I'm going to, again, like the previous problem, just make the math easy for me without having a calculator. So I have this number here changes the same exponent, and you don't have to do this. You just plug it in your calculator and you'll get the same answer. But I'm doing it to make sense. So I have 150 times 10 to the 23rd. I know each mole is 6.02 times the 23rd. I'm kind of leave this 2 off here. So what I'm going to do is divide 150 times 10 to the 23rd into groups of 6 times 10 to the 23rd. This is my grouping size, so I'm dividing this up into groups. And these guys cancel out. And I'm essentially dividing 150 by 6, which is 30 moles. Now you could use dimensional analysis, that's fine. You'll get the same answer. So I have 30 moles. Well, each one weighs 18 grams. So I do 18 grams 30 times for 540 grams. Okay. And you could do dimensional analysis again, would be simply take this number, multiply it by 1 over 6 times 10 to the 23rd, and then which you'll end up with 30 moles, and then you take that 30 moles and multiply it by 18 grams per mole, and you get 54 grams. So hopefully you'll see that. So the dimension analysis written out would be 1.5 times 10 to the 25th times 1 mole over 6.02 times 10 to the 23rd. And then that's this answer up here. I'm just doing this because it's another way of doing it. And then the second part is you take this answer here and then multiply by 18 grams per mole, and you get 54. So here the atoms, the molecules will cancel out, moles will cancel out, end up with grams. So this is thinking of it conceptually, and this is doing the dimension analysis. Okay. All right, so what I'm going to do, I'm going to send out a worksheet, and the first set of problems on that worksheet will refer this PowerPoint. Okay. And I'll do another PowerPoint going over figuring empirical formula, a molecular formula from percent composition. That'll come next.